Hello everyone and welcome to this lecture. In our previous lecture we saw how we can solve a homogeneous second order ordinary differential equation with constant coefficients, and today we're going to see an example. So this was our equation, the differential equation, and we saw that the general form of solution had taken a form like this, where C1 and C2 are arbitrary constants and R1 and R2 are roots coming from the auxiliary equation. So if you recall, the auxiliary equation for this differential equation was AR squared plus BR plus C equals to 0. And you can see that I have written down a differential equation. So if you just look at this equation and compare this one and this one, you can easily see that A is 1, B is -1, C is -6, right? So the auxiliary equation will have this format: AR squared plus BR plus C equals to 0, and we need to solve that to get two values of R, because in this example you will see that this R1 and R2 they are not equal. So let's try to solve this auxiliary equation first. This is just R squared minus R minus 6 equals to 0, and it has two solutions, that is R plus, sorry, it should not be R plus. One of them is just plus 2 over here, and then you'll have R minus 3 over here. So R equals to 2 or R equals to 3. So let's call R1 as 2 and R2 as 3. Sorry, this should be minus 2. Yeah. So this is my two roots, and using this solution I can easily write down the solution yt as C1 e to the power R1, that is minus 2t, then C2 e to the power 3t. This is done. This is the general solution, the GS. Now if I now fix two boundary conditions or two initial values, that is when y of 0, the derivative of y with respect to t when evaluated at 0 is 8, and y of 0 is 1, and using these conditions we can trace out a particular solution. So the particular solution will come from the general solution plus the conditions, that is either boundary value conditions or initial value conditions. So just like before, we have to find the C1 and C2. So let's first use this one. So when t equals to 0, you have 1, so that should give you 1 over here, and if you put t equals to 0, this is just C1 plus C2. This is one equation. And if you evaluate y prime of t like this, then you will have minus 2 C1 e to the power minus 2t, and then you will have 3 C2 e to the power 3t. Now put t equals to 0, and this part becomes minus 2c1 plus 3c2, but since these conditions are the conditions that we're applying onto the differential equation, on the solution to be precise, so this will become 8, right? So now you have two equations as c1 c2 is equals to 1 and minus 2c1 plus 3c2 as 8. Now what you need to do, you just need to solve for c1 and c2. If you do that, the solution will be c1 and c2 are respectively minus 1 and 2. So our particular solution, that is PS, is just minus e to the power minus 2t plus 2 e to the power 3t. This is how you can easily solve when the roots are distinct. So let me just again, this example, roots, that is this R1 and R2 are distinct. that is R1 not equals to R2. Next, we would like to see a case of R1 and R2 to be equal. That is, we want to see cases where these two roots R1 and R2 are the same. So let's try to do it. Okay, next case, we want to see what happens when R1 is equals to R2, and we can do it in a general way. So again, consider the equation ay double prime by plus by prime cy, this is equals to 0, right? Just like before, this one. And now the auxiliary equation, so let me write aux equation to denote the auxiliary equation, is just ar squared plus br plus c equals to 0. And since we want R1 equals to R2, we are demanding that b square minus 4ac is 0, right? This is the thing that we are requiring. And if you require that, then instead of typing R1 and R2, let's call it just R0. So the auxiliary equation will now be br0 plus c. This R0 is just a notation that it's denoting the fact that R1 and R2, they are equal. That is the repetitive characteristic roots. So again, let us choose a solution. y1 of t as e to the power r0 t, because this r0 is a root, right? So that's why we are calling it, this is one of the solutions. The second question we ask, what about y2 of t? Because this is a second order equation, we are supposed to get two linearly independent solutions. The thing that will happen right now is that to find a second one is not simply a constant multiple of y1, because if you remember in our past lectures, we call that if y2 and y1 are independent of each other, that is two functions that are independent of each other, they are not just simply a scalar multiple of each other. So y1 and y2 cannot be written in such a manner that, let's say, if you want y2, it can be written with some alpha y1 where alpha is a scalar. Instead, now what we'll choose is that we want to try a solution of the form y2 is this function which depends on some function u of t. This is also a t dependent function, and then we want to put y1. So instead of y2 is equals to alpha y1, we just made the following adjustment. We just made this whatever is appearing over here time dependent, that is the variable dependent. So let's just write like this. Also, let's cross this out so that you guys don't get confused. So if you do that, if you choose such y, so this is also called a trial function. We are trying this, that's why we're calling it a trial function. And if you just take the first derivative, this will just be u prime e to the power r0t plus r0u e to the power r0t, and then the second derivative will be u double prime plus 2 r0 u e to the power r0t plus r0 squared u e to the power r0t. This is just differentiating with respect to time, that is t. You can call it time, you can call it another parameter, but for physics people, this is just time. We are just thinking like that. And since we also want y2 to be a solution of the equation that we're dealing with, that is the second order equation like this, you can put that this y prime and y double prime over there, and what will happen is that you will get some conditions out of that. So let's try to do it. So we are putting all this y2 prime, y2 double prime into our main equation over here. Since we are assuming y2 is something that will satisfy this equation, so let's do it. So let me write a y2 double prime plus b y2 prime plus c y2 as a. Now I'm just putting the values that I obtained over here. So this will be u double prime plus 2 r naught u e to the power r0 t. Oh yes, I forgot to write e to the power r0 t over here. So here, instead of writing like this, I want to factor this out. So I'll do that. That will be more convenient. So u double prime r0 to r0 u prime r0 square. Then I'll have my u, and then I'm factoring this e to the power r0 t. Then you will have b u prime plus r0 u e to the power r0 t. Then you will have finally c u e to the power r0 t. Now you need to do some algebra and gather the terms for u double prime, u prime, and just u. And if you do that, then you will find a u double prime plus 2a r0 plus b u prime plus a r0 square plus b r0 plus c times u, and I should have written it like this. Okay, so let me just start from the left side so that I can cover the whole screen. So yeah, so this will be a u double prime plus 2a r0 plus b u prime plus a r0 squared b r0 plus c. Now we have our u over here, and we are factoring this e to the power r0 t. And now if you notice that this can be written as follows, because you see that using this whole thing that we wrote in terms of u, this will just reduce to a thing that is u double prime of t would be 0, and the reason for that can be found with some rationale that I'm going to present right now. Now, as we were saying that we have to find out something from here, and that will simplify our results, and from there we can impose some conditions on u double prime or u prime or u. So to do that, what I'm going to do is that I'm going to use some information that we saw earlier. That is, one of them will be this one, this auxiliary equation. And if you use this auxiliary equation over here, this huge expression, you can see that this guy actually is 0, and because of that this whole term over here is going to 0 now. So this is 0, right? So what about this term? If you recall that this r0 was coming from the fact that b square minus 4ac is equals to 0, right? So what does that tell us about r0? That means two roots were equal, and that means this is just b by twice a. So 2a r0 plus b equals to 0, right? So this guy is also 0. We got a really simplified result. So finally we can write it as a u double prime e to the power r0 t. But we assumed on the very beginning that y2 is a solution of the differential equation. So this part over here, let me just highlight it out. So this part over here will also be 0 because we assumed y2 is also a solution of ay double prime plus by prime plus cy equals to 0, right? Okay, so this means here we'll have a 0 because this guy will go to 0, so that means on the left hand side 0, and on the right hand side we have something like this, and I'm just writing the left hand side over here. Instead of writing 0 over here, I just wrote it over here. So, and a will not be 0 because if a is 0, then our equation is no longer a second order equation. So e to the power r0 0t cannot be 0 for any constant r0, because that would mean that t is going to minus infinity. So we are saying that u double prime is 0. That means the most general form of u of t will take alpha 0 t plus alpha 1, where alpha 0 and alpha 1, alpha 0 and alpha 1 are arbitrary constant. Now, is this it? And the answer is no, because this alpha 1 will produce y1 again. So what you need to do is that you need to just take this part. So this is the only relevant part. And the way to see that this alpha 1 will produce y1 again is to just take the linear combination y1 plus y2, and if you write y2 as ut e to the power r0t, where y1 is itself e to the power r0t. So let me just show this small thing to you. So let's write it like this, right? Forget the arbitrary constant that appear over here, that is c1 and c2. So y1 was e to the power r0t, right? And y2 is just alpha 0t, that is u. I'm writing the u expression first. This is our u of t, and then we have e to the power r0t. So you can see that up to a constant, that is if you take this whole thing out, that is you multiply and simplify, this is just 1 plus alpha e to the power r0t plus alpha 0 t e to the power r0t. So this is just this is just similar to a c1 y1 again, and this is similar to a c2 y2. So this is this alpha 1 is just reproducing the y1. So that's the justification. So the only part we will need is this alpha 0 t relevant part. So finally we can write down the full solution as, so full solution y of t is equals to c1 y1 plus c2 y2, where y1 had a form e to the power r0t. So let me just emphasize this thing again, and this was alpha 0 t e to the power r0 t, right? So let's write it down. c1 e to the power r0 t plus c2 alpha 0 t e to the power r0 t. Now you can take this e to the power r0 t common, that is factor it out. You can write this as c1, and this c2 alpha 0 can be rewritten as c2 prime, and there is t. So this is the most general solution whenever there is a repetition of roots for second order ordinary differential equation with constant coefficients. So let's see a very short example, a numerical example that is. our equation is y double prime plus 4y prime plus 4y is equals to 0, right? And what is the auxiliary equation? So the auxiliary equation is r square plus 4r plus 4 equals to 0, and it has two roots, r1 equals to r2 equals to minus 2. So let's call this minus 2 as r0, and you just use this fact, this solution. So our general solution will be just e to the power minus 2t c1 plus c2. You can give a prime, you cannot give a prime, that's up to you. So these are just two arbitrary constants, but there is a t over here, and that's it. You are done. And the last case that we are going to consider is that when r1 and r2 are complex. So this will be a last case for today. Notice that for a differential equation that we are dealing with so far now, the auxiliary equations are coming as ar square plus br plus c equals to 0. It might happen whenever b square minus 4ac is less than 0, the roots will be complex. But we said that a, b and c belongs to set of real numbers. So they are real numbers, right? The only way that is possible is that this r1, if this is a complex, let's call it lambda plus I mu, and if r2 is coming in the form of lambda minus iu, that is r1 is equals to r2 complex conjugate, only then you can have this a, b, c as real parameters. Because if you recall from your high school that these coefficients over here, that is b by a, can be written as the addition of the two roots, alright, and this c divided by a can be written as the multiplication of the two roots. So the only way you can have real numbers in the auxiliary equation and the roots being complex number is that the two roots that will come from the auxiliary equation will be complex conjugate of each other. And how do you solve this again? Since they are distinct, because these are complex numbers but they are distinct, right? They are not the same. So the general solution we wrote as e to the power r1t plus c2 e to the power r2t. But now what you need to do, you just need to put these complex values. So c1, instead of r1, now you'll have lambda t plus e to the power I mu t, and here you will have c2 e to the power lambda t, and here you will have a minus I mu t, like this, right? Now you can do some simplification, that is take e to the power lambda t outside, you have c1. Now if you look at this e to the power I mu t, and this is some identity, the Euler's identity from your high school, that e to the power ix is equals to cosine x plus I sine x. So here instead of x we have mu t, so this will be just cosine mu t plus sine mu t, and there will be I over here. So you have c1 cosine mu t plus c1, there will be a I sine mu t, and from this part you will have c2 cosine minus mu t, sorry, not minus, sorry about that. You have a e to the power minus I mu t. So if you just put a minus in front of this I, this affects this plus sign over here and becomes a minus sign. So when you have a e to the power minus I mu t, you will have cosine mu t minus I sine mu t. So the rest of the terms are just minus c2, obviously there is an I, and sine mu t, right? Now to simplify further, we are going to collect the coefficients in front of cosine and sine. So let's try to do that. That will be just c1 plus c2 and we have our cosine mu t, and finally you will have plus I, then you'll have c1 minus c2 sine mu t. So this is the most general kind of solution that you can have, but you could also write it like this, that is, you keep these imaginary parts over here. There is no harm in doing that. So this is how you can easily solve second order differential equation, the homogeneous ones with the constant coefficients. And if you are wondering what is an example when my roots will be complex number, a very simple example is the harmonic oscillator system that you see in your day-to-day physics, because the auxiliary equation is what? R square plus omega square, right? Sorry, not omega square over here, it should be just omega. Oh no, sorry, it should be omega square. Yeah, my mistake. And you will have R is equals to plus minus omega. So it really doesn't matter. It will be by something k by m, and omega is equals to square root over k by m, if you recall from your physics class. So this will be just R is equals to minus omega square R square, and finally you will have R is equals to I plus minus omega. Sorry, not like that, not like that. Oops. So let me write it in an organized manner. Previously it got a bit disorganized. So minus omega squared, so this will be just plus minus I omega. So you can see that there is no real part, so lambda would be 0, and you can just put in the imaginary part and get your solutions. So this is how we covered all the cases for second order homogeneous differential equation, that is ordinary differential equations. We saw 3 cases where the roots can be distinct, where the roots can be equal, and the roots can be complex conjugate of each other. And from the next video we are going to see that how we can deal with non-homogeneous second order ordinary differential equations. This will be it for today, and thank you.